Okay, so for 7.6, I thought we'd take things in a slightly different direction. So this section talks about how to use a table of integrals and or how to use a computer algebra system to calculate integrals. Now, those two things, what we're really talking about is the technology that we have on hand to perform what's called symbolic integration. And to do that, we have, so really, in terms of what it means to you, the tool that we have that allows us to use that, so the tables that we're going to use in this class, I highlighted some in the page for this section that are from the internet. Some of them are one of them is created by somebody who's retiring actually in the next few months, and so I downloaded the PDF, which is free to use for anybody, but that web page will soon be gone, and it's actually a really great resource. So it's sad that that's happening. And as for computer algebra systems, your calculator, your TI-84, Wolfram Alpha, and even Desmos, I think, will do it for you. All of those are examples of computer algebra systems. They're going to perform the symbolic integration. So you put in a function, and it'll give you an antiderivative for that function, like explicitly. So that task actually has a very long and fascinating history, and I won't touch on the philosophical debate on whether math is discovered or math is created. Regardless of where you land on that debate. Fundamentally, though, the history of math, as well as, more specifically, the history of symbolic integration, is about people. It's about the people who helped develop the tools and techniques that we have. So as I'm going through here, you don't have to take notes. You don't have to, follow along too carefully. But for your mathematical development and for your enrichment, I'll be talking a little bit about how we got to this point in our history where we can do things like computer algebra system. So the first thing you have to keep in mind is there was an era before calculus, and not in the so that is true in the strict before Sir Isaac Newton and Gottfried Leibniz formulated calculus, but we mean also in the sense that this was before the time when we were doing rigorous math. So the first person I want to highlight here, since we're talking not just about instead of talking about the area under the curve, which is where this problem originated from, right? So, where we said it started out with, we're going to approximate with, all sorts of shapes that we can stick underneath the curve. No, in fact, what we're talking about here is numerically, symbolically. How do we integrate something like find the area under the curve of a polynomial? And so the first person that we're going to highlight here is Hassan ibn al-Haytham, circa the 10th century Common Era, so around 1000 CE. Okay, you may know this if you have any knowledge of these the golden age in the Islamic civilization, where there were a lot of advancements actually in the Middle East, mostly because the government, overseeing that caliphate was actually really invested in funding advancements in astronomy. Yeah. So what this person was able to accomplish was something called the sum of fourth powers formula, which is directly applicable to finding the volume of a paraboloid. So if you think about a parabola and you rotate it in this third dimension, it looks kind of like this bowl shape. This formula helps you find the volume of that. So we had something like this more than 1,000 years ago. Other advancements that came, not too far removed from when calculus as a subject was finally introduced in the 17th century. We have Bonaventura Cavalieri, who introduced this quadrature formula, the integral from 0 to a of x to the n dx equals 1 over n plus 1 a to the n plus 1, for n being greater than or equal to 0. Now, the way this was formulated, and this is important if you ever go on to take a history of math class, we're using modern notation. They weren't. Okay, so Cavalieri didn't express it this way, but it's equivalent to writing it this way. Because as you know, or you may not know, and you're going to learn right now, the integral symbol was introduced by Leibniz. So that's where we, move into, okay, so with the development of calculus, right? So we have Gottfried Leibniz, a German mathematician. Cavalieri was Italian. And we know Sir Isaac Newton. If you don't know, so one really cool thing, or I guess important for historical context, you're like, how do these people have the time to think about this stuff? They were paid by, well, in the case of Sir Isaac Newton, by the Royal Academy of Sciences, which is literally funded by the Royal Treasury. So like the King of England was like, yeah, you can have this money to do math or whatever. I'm simplifying like ridiculously, but that's basically the idea. Okay, so them two separately, by the way, not at the same time, not in any collaborative form like we would do them nowadays. They of course came up with the fundamental theorem of calculus, which we learned at the tail end of Calc 1, right? So basically, writing it all succinctly, we can write it as the integral of f prime of x from a to b is f of b minus f of a, which is, assuming f prime has an antiderivative. Okay, so there were improvements that to this original form that started right away. So it extends the notion of integration beyond a function of one variable. That's one of the topics of Calc 2 and Calc 3, Math 402. So keep an eye out for that. Okay, so now let's talk about how technology has helped us do integrals. Okay, so symbolic integration, doing the integration by hand. If we want to talk about introducing technology, obviously computers came later. The first tech tool that was introduced was what's called a table of integrals. Okay, and what this really is it's just a book that anybody can reproduce and purchase or sell, that contains all sorts of standard formulas of integrals. And so if we're going to start with the very first recorded table of integrals, that anybody was successful in marketing and putting out into publication. Meyer Hirsch, um, a German or a Prussian, I guess you would say in those times, published the first edition of a table of integrals in what is now Germany. That was actually then exported to the UK in 1823. So they got their first copy of this in 1823. But other competing versions emerged, and some of these became what's called like definitive editions. Okay, so then we have David Bjorn de Haan. By the way, if this is, it feels, this maybe feels like really dry and like, okay, why are we learning about these crusty old dead people? Because I want to, hint at what's coming ahead. The history of this is super rich. So remember, we started with actually something that came out of the golden age and of the late Middle Ages Islamic Caliphate, right? We're moving into, this was purely Western European endeavor. And then we see how it's taken over by the Americans, right? And it directly is applied and used by NASA and by Black women who were considered calculators. I'm getting ahead of myself. I need to stop. So it's super cool. There's so much to see here. So David Bjorn de Haan, a French man, he wrote Table d'intégrale définie. And you don't need to speak French to know that this means tables of definite integrals. And I used to sort of know French, but not anymore. Anyway, this he wrote in 1858. And this kind of became like the definitive model for tables of integrals moving into the early 20th century. In the early 20th century, we have basically the standard becomes Gradstein and Rijnik. I don't know how to pronounce that. I'm sorry. I'm trying my best to pronounce that. So their table of integrals actually becomes the standard in the 20th century and reproduced and used by all sorts of organizations. Nowadays, we have other, all sorts of tables, even people using, creating them by hand and publishing them on the internet. But that kind of leads into, what you would expect is, when did the computer algebra systems come up? So before we get into that, though, we should talk about how this was used, like why they needed tables of integrals, right? So the very first interesting application that I could scour is the development of Fourier analysis. So Fourier, who was a French mathematician, developed a theory of heat conduction. So think of heat, right? It's energy, the thermal energy, and the way that it propagates. He modeled using what's called Fourier analysis now. And that directly leads into the development of the ordinary and partial differential equations. Those of you who are going to be engineers may need to take these classes. These are not complete theories, by the way. Only a very small segment of partial differential equations can be solved. The vast majority of them are still an open question. And then that leads into somewhere in here, all this is used to calculate orbital mechanics. So how things orbit around celestial bodies like the moon, the earth. And somewhere down the line, that leads to the Apollo space program. Okay, this is where it gets really interesting. Okay, so how the tables of integrals were used were literally people would sit down, need to calculate something that involves an integral, and would do it by hand, just like you and I are doing, in the last few sections. But they needed to do hundreds, thousands of them to calculate something related to, for instance, the first orbit of a person around the Earth, right? So these tasks, though, the mathematical computations were literally handled by what we called human computers. So people that were paid, hired to compute things, okay? And it's not like it was just some, you needed, you were just cranking out calculations. Like, this involved a lot of critical thinking skills. And among these were the mathematicians Katherine Johnson, who most people are familiar with Katherine Johnson through the novel and the film based on the novel, Hidden Figures. So Katherine Johnson and Dorothy Vaughan are two of the more well-known human computers. Dorothy Vaughan, by the way, was instrumental in the application and implementation of the first actual computers. So, like physical programmable computers. She was the head of that division at some point. And this led to a variety of accomplishments for NASA, including the first orbit of Earth, before that, actually launching a person into space, Alan Shepard, the first orbit of Earth by an American, John Glenn, and, of course, the 1969 moon landing. So, and I'm not being hyperbolic, like literally, this was only accomplished through the use of being able to calculate integrals. Okay, so now that I've alluded to it, computers. So this also probably is going to be your first, brief informal history of computers themselves, unless you've taken some computer science class before, and they covered that. But again, for your mathematical enrichment, let's actually talk about computers. So early computers, they actually existed throughout human history. I wish I had the specific details of some of these, but they're actually really fascinating, have been encountered in cultures all over the world. So some of the first ones that were used, the early computers, were mechanical. I mean, strictly speaking, mechanical, right? So you have our first example is a differential analyzer. In the 19th century, that used wheel and disc mechanisms. So you just kind of like let it go, charged it, and then using a wheel or a series of wheels and discs, it would perform an integration. But to formally turn these mechanical computers and to come up with a comprehensive theory about how to create these things, you need to look no further than Ada Lovelace. who was also related in the form of marriage to Charles Babbage, who is frequently cited as the first computer scientist. Actually, it's Ada Lovelace. Ada Lovelace did the majority of the important work there. So very fascinating story with her. So she, like other female mathematicians of her time, were hampered by the gender norms and patriarchy that prevented her from actually carrying out her career the way she wanted to. But she did accomplish a great deal despite that, including developing the early theory of computation, so what it means to create a computer. And it is important also to acknowledge that the tools of math were used in the early 20th century, including the earliest computers, were used for war. And this means, positive and negative things, depending on how you look at it. For instance, the Nazi regime in the 1940s developed the Enigma encryption machine, and that was to encrypt messages from the commanders to the front lines. In that same time period, the Allied forces developed the Colossus code-breaking machine. There were other methods for code breaking. For instance, in the Pacific Front, or the Pacific Theater, I should say, Navajo speakers were used to code break. So they allowed Allied forces to de-encrypt messages passed from the Japanese military leadership to the front lines. Okay. Other things that came out from this were, for instance, what's called ENIAC, the Electronic Numerical Integrator and Computer. It literally says, so Electronic Numerical Integrator and Computer. From 1943 roughly to 1945, this was developed. And one really instrumental name here, Grace Hopper, who was responsible for the first programming language compiler. So a massive leap in development in terms of computer science, actually, in this moment. I'll go back for a second. The Colossus code-breaking machine, one of the really instrumental people here was... Oh, I'm blanking on the name. Alan... Oh no, I'm blanking on the name. Alan Turing, duh. So Alan Turing, a mathematician from the UK, who also was identified as homosexual and was closeted, but was outed by his own government in the 1950s, was forced to take hormone injections that he did not want, but he did that instead of being imprisoned, as homosexuality was against the law in the UK in the 1950s, and so tragically he died of suicide in the late 1950s, rather than being celebrated as the brain behind the Colossus code-breaking machine. Very sad story there. Only in recent times has Alan Turing been revindicated, I guess. Not that there was ever any need. He didn't do anything wrong. Right. So, all right, moving forward. Grace Hopper. Okay, so with the development of transistors too, transistors being circuit elements that allow you to create integrated circuits, this is really where computer technology took off. Integrated circuits, by the way, some instrumental organizations behind these, Texas Instruments. Which leads us finally to computer algebra systems. So once computers were sophisticated enough to actually be able to do symbolic integration, the earliest computer algebra systems, which were just programs that allow somebody to perform symbolic mathematical operations. And there's a wide variety of these. So it's not just, integration and differentiation. There's a lot that can be done with these. We have Skip, in 1963 by Martinus Vetman. And right on the heels of that, Math Lab, not to be confused with MATLAB, which is a programming language, and also not to be confused with My Math Lab, which is a proprietary program to do online homework. This was made in 1964 by Carl Engelman. But nowadays, what do we have? We have other tools. So, for instance, the more sophisticated ones modern tools. The sophisticated ones that we could use are Mathematica, which is produced by Wolfram. Wolfram is a company that handles such tools as Wolfram Alpha. And yes, it is integrated with Wolfram Alpha. So if you are using Wolfram Alpha to perform any sort of calculation, it is in fact using Mathematica. So it's super cool. You're like plugging into a kernel of Mathematica. There's also Maple by MapleSoft. You may have guessed it. This is from Canada. And there's also Sage. Sage is a newer one. Now, all of these are proprietary, so you'd have to purchase the product in order to use it. If you go on to do university mathematics, your university may have a license for these on your university computers. So there might be a lab where you can use a computer that has Maple or Sage or Mathematica. But you'd have to ask. And for us, well, your TI-84 or whatever TI calculator you happen to be using will probably have a computer algebra system that allows you to do integrations and differentiations, but it's much less powerful than these tools. Okay, so the more you know, that's basically it, right? So